That's me. And that's 3 people. And I'm going to help them. But it has to be something really big. Something they can't do by themselves. So I do it for them. Then they do it for 3 other people. That's 9. And I do 3 more.
That's 27, so I'm not really good at math, but it gets big really fast.
This video is a continuation of other videos, so if you don't feel comfortable with the time value of money, time equivalency, and how to do analysis of present worth, then you may want to go back over those, because we revisit the concept of growth and the interest impacts of a single payment and then multiple payments in order to segue to both arithmetic and geometric gradients, where we have 2 different types of growth occurring simultaneously. Let's consider that we're going to make a single payment. We're going to make one payment in time 0 of $100. So here we are right now, time 0. We put in $100 at 10% per period. It could be years, quarters, months, whatever, 10% per. Then our 100, one period later, it's going to be $110. Then 121, then 133, right? As we gain 10% each time. And we could calculate any of those, right? This is a single payment, and we're going to calculate the future value of that in whatever period we want. So the syntax would be f given p, I, n. You can look up those values in the table or just calculate it from the formula, right? Which is why you see 1 plus I to the nth. So if we said n equals 100, then the future worth of $100 put in an account right now, 100 periods later, you would have 1.38 million. And so this is to make clear the time impacts from interest on a single payment. Now let's look at what happens if you have a series of payments instead of just one. Right, so as with previous, we're going to put in $100 in the first period. Last time we put it in period 0. We're putting it in period 1, so I'm depositing $100. Right? And then I'm going to make 10% on my money. So that 100 becomes 110. But in period 2, I'm also going to deposit another $100. So now I have the 100 I put in plus the 110 from the interest gains on the previous payment, so I have 210. Similarly, the year or the period, whatever the case may be, after that, then I have 331 because I've gained interest on period 2 amount plus the 100 for period 3. And then it just continues on like that period after period until we get to period n, right, whatever n may be. And then if we want to solve for that, then we would use the formula that you see here, which is actually f given a in syntax. So of course you could look it up in the table or you could use that formula. Either way, you'll find that in the 100th period, if we were going to say n equals 100, then you would have 13.8 million accrued from all of those payments and the interest effects. So we just covered what interest does to a series of payments and how it increases the value of those payments over time. But what happens if the payment that you make increases itself? So in period 1, we put in $100, but in period 2, we decide to increase that to 105, period 3, 110, and so on. So we just keep increasing it by $5 each time. Now that equation you see is specific to this example that I just made up. It's not going to be every problem. But the point is that we're increasing our payments this time instead of making equal and even payment. So in the 100th period, I would put $595 into this account, right? Or my payment would be $595 considering that I've increased it by $5 every period for 100 periods. So I'll draw that in, $595 in period 100. Now this leads us to wonder then, what happens once we include interest, right? So now we're going to have interest effects on this series of increasing payments. So here are a series of payments up to period N. Right? We're still looking at an interest rate for illustration purposes of 10% per period. So like before, we put in our first $100 payment. And we're going to gain interest on that first $100 payment, so it becomes 110 in the next period. But now I'm going to put in 105 in the second period, 110 in the third period. So it's different from the previous example that we saw when we were considering interest. So now I got 110 based off that first period. And then in the third period, I'm going to have the interest effects of all of this, which would be 215, which is the 105 and the 110. So my payment plus the interest from the previous period. So of course now I have 236 from the previous plus 110 this time as a payment, which goes forward. And then this whole series or this cycle keeps repeating and repeating until you get to whatever period you want, the nth period. Now I snuck in the name of this, which is when you have a payment series that is increasing or decreasing by an even amount, then that's an arithmetic gradient. Now we have a gradient, right, that's building upon itself with interest effects. So I'll draw a positive gradient here, similar to the example that we're working. And in the table, you'll see that they have a diagram, which I'll go over, and they show a negative gradient in the table with the formulas. So here we have a positive gradient increasing by $5 each time based off the same payment amount. So I'm going to draw a triangle, right? And you'll see, of course, that it has the same slope all the way across. That's one way to remember arithmetic gradient. Now you can get the value or the factor of this arithmetic gradient through a table, wherever your table source may be, or from a formula, just like before. Now if we take a look at this clip from a table, you're going to notice that there's the formula and that there's only a present worth or an annual worth. There is no future given arithmetic gradient. There's a present given arithmetic gradient and an annual or annuity, a uniform series, given arithmetic gradient. So if we were trying to find the future worth equals what, then we would have to either solve for the present or for the annual or annuity, whatever, the uniform series, and then convert to the future worth. So let's say I'm looking for this series, this gradient. I'm going to find the present worth, and then I'm going to say, and I'm going to convert that to future worth by future worth equals whatever the amount is that we solve for, f given p. Taking a look at the table with the formula here, you can see that they gave you a negative gradient, whereas the problem we're working has a positive gradient. But either way, it's broken down into this annuity, this uniform series, right? So here it would be 100 for us, right? Every period we are paying 100, 100, 100 plus the gradient amount. So we're paying $5 more each time. So our gradient is plus 5, whereas in the diagram they're showing something going down. And you can solve it either way. The important thing to remember, and one of the things that I encourage you to do, is to draw this triangle. So here's our gradient. Right? And when you draw that triangle, that will help you to ensure that you get the proper placement of P given G. Right? So here I'll draw what we have, which is a positive gradient, onto the diagram in the table, and then draw out my triangle. The reason I do that, because P given G is always one period before the first increase, not the first gradient amount, but the first increase. So you can see in period 2, there's the first gradient amount, but the first increase occurs between period 1 and 2. So there's my triangle, and then P given G, always one before that triangle, and that puts me, in this case, in 0. So to make sure we have this down, and to clarify that, let's look at our problem. So here, you can see our payments of 100 occurring every period, whether the period's years, quarters, months, whatever. We're putting in 100, 100, 100 every period. And then we have our gradient, whereby we are putting in 5, 10, 15, 20, whatever, all the way until we stop. So let's draw in our triangle, and then remember that P given G is always one period before the base of that triangle. All right, so now we're going from 0 to n. So it'd be P given G I n. So if we were going to solve the present worth of this, there would be two components to it. It doesn't matter whether you do the annuity first or the gradient first. So here I'll put $5 increase, right? So we're doing the gradient portion of it, and we're going from n to 0, right? So n minus 0 is n. So if it were 100, we would put 100, whatever the case may be. So let's say we're doing 100, so then 100 periods plus, that's not the end of it, because that's only the gradient portion. Now we still have to do the payment portion, which was originally our 100. So now we add in our 100, P given A, 10% for 100 periods. And then that would be our present worth. So let's look at an example. Let's say I'm going to invest $20 and then $25 and then $30 and so on every month for 4 years. I'm going to make 1% per month on this investment, and I want to know how much am I going to be paid back at the end of 4 years. So if we're going to draw this out, it would be future worth in month 48 equals what at I equal to 4%. Our payment amount is 20 per month, right? And then our gradient is plus $5 each period, which in this case is going to be months. So this shows our payments, right? 20, 25, 30, 35 every period up until period 48. And then at the end, a withdrawal. Since we're putting money in, we're spending money to get this investment back. They're going down, whereas we would expect a positive future worth when we remove this. We're going to draw this out as a cash flow diagram. So now let's break down this payment system into its two components, right? One is the annuity that's occurring evenly, and then the other is the gradient that increases per period. Right? So obviously, as we've written down, the annuity itself is 20, right, which I marked with those slashes, and then we have the 5, 10, 15 as the gradient. If I were going to draw this, I would draw it out with my triangle and then verify that my P given G, arithmetic, is where I want it to be, which it is, in period 0. So this is the present worth. So now let's solve for those two different components in order to find the present worth. First is the annuity, the annual worth if this were annual, but we're dealing with months here. So present worth is 20 P given A, 1%, because that's our interest rate, for 48 periods. Right, and then the second one is the gradient, and now we're going to be increasing by 5 every time. So it's going to be plus 5 P given G, 1% for 48 periods. To make this faster, I worked this out below so we can take a look at it. And what you'll see is present worth, right, is the gradient component. So there's the gradient component plus the annuity, right, the uniform series. So that's A, P given A. And then once we solve for all that, we're going to have a present worth. So we got to move that present worth to the future 48 periods. So I have F given P 1% for 48 periods. So let's say instead of $5, right, instead of increasing our payment by $5, now we're going to increase our payment by 5%. So whereas before it was 20, 25, 30, 35, now it's going to be 20, but then it's going to be 20 times 1.05, which is to say increasing by 5%. And then the next one would be 20 times 1.05 times 1.05. And so now every time we're increasing by 5%. So now we have this geometric growth. We have this exponential growth going all the way out to month 48. So if we were to go to our tables, you would see that the geometric gradient doesn't have factors in the table. So we have no choice but to use the formula, the equation, to solve for a geometric gradient. And as before, it only has present worth. Before, with arithmetic, you can solve for present worth or annual, but now with geometric, right? So exponential growth, we can only solve for the present worth. And we have two different rates. We have G, which is the gradient rate, the increase in the gradient, and then we have I, which is the interest rate. And so we have interest growth on top of geometric or gradient growth. To represent that in syntax, it would be P given G, right? But it would be present worth is equal to P given G, but note what goes before the P given G, which is A, the annuity amount or the uniform series amount. So if we were going to solve this, because all of the geometric growth is based on that amount, right? Before it was 0, 5, 10, right? But now it's 20, and then it's 20 times something, and then it's 20 times something. So you got to start off with that uniform series amount, and then put in P given G. This is geometric, right? And then you would have the geometric rate and the interest rate. Oops. So this should be G, and then I, and then N, just as before. And then when it comes to finding that factor, if you were to go to the tables, as I mentioned, they're not in there. So we have no choice but to use the equation here. So there are two options, one for when G is equal to I, and one for when G is not. In our case, we're dealing with a 5% gradient growth and a 1% interest rate, so we're going to use the one that is not. Going back to our cash flow diagram, right, this is what it's going to look like, and it's going to keep going out until period 48. So we're going to have P given G, geometric, right? And we're going to solve all of that and then move it forward to find the future worth in the 48th period. So now let's look at how we solve that, right? So we put in present worth is remember, it's the uniform series amount, the annuity amount, P given G, G-I-N. So for our example, we have $20, and then we're increasing $5 per period. So 20, 5%, and then we have 1%, which is the interest rate, and for 48 periods. If we go to, we notice that G is not equal to I, so if we go to our table, then we can find the formula. So there's the formula that we would use, that's where that comes from. Put into here, and then once we solve that, again, we got to move it to the future because we want to know what this is worth in period 48. So that's the present worth of that, F given P. So let's look at this example. I found this one on the internet from this book. And we have an engineer planning for retirement. In order to supplement the pension and offset effects of inflation, this person intends to withdraw $5,000 at the end of the first year and to increase this withdrawal by $1,000 at the end of each successive year. What we're doing is cutting $5,000 out of this. Right? Cutting $5,000 out, and then we're going to have this consistent slope like this. Right? And so when we use, first question is this arithmetic or geometric? We would recognize this to be P given G, arithmetic. So that's why I drew my triangle, right? So there's my triangle, and it's one period before, so that puts me in time 0, which is very convenient. So the first part of this is we're going to calculate the present worth of this part, and then we're going to calculate the present worth of the gradient, and then we're just going to add them together for the total present worth. So this is what it would look like. Here's all of our payments over those years. We're at 6% for 15 years, and our annual amount is 5K. We're going to increase these, right? So here's a triangle. One period before that, times 0, very convenient. So we're increasing by 1K with an arithmetic gradient, 6% for 15 periods. All we have to do then, add those together. Now, instead of using any formula, especially those long ones, I'm going to do what? I'm going to go to the tables, and in the tables you can find arithmetic gradients. I'm going to use P given G, and I think our period was 15. So that would be the factor for P given G. Solving this all the way down, that factor that I just pointed out for P given G, you will see is right here. Since we're dealing with 1K, then it just comes out to that. This factor is, of course, P given A at 6%. So if we were to look for that one, P given A, 9.72. So it'd be right here. Right, and that's where that factor comes from. This time we're multiplying by 5 because the annual worth is 5, so we get our two numbers to add together, and we get 106.114. Incidentally, they do in this book solve this problem, so if you'd like to see how they solve it, they do it a little differently. There are always many ways to solve problems, so not necessarily is one way the way to do it. And you can see that here because they use P given A, right? This is the 5K that we're paying. And then for their gradient, they elect to solve it or convert that gradient into annual worth. So they convert that gradient into annual worth, and then they have to convert that annual worth into present worth. So they added a step in there that I don't have. Why they chose to do it that way? Maybe they really like annual worth. So here's another example. I want to remove $500,000 a year from an offshore account, and I want to do so for at least 20 years. So I want $500,000 a year for 20 years. I can put $2 million in an investment account right now and earn 6% on it, and I can increase how much I put in that account each year by 6%. So I can put $2 million in year 1, and then $2 million times 1.06 in year 2, and so on. So the question is, when can I start withdrawing my 500K and stop investing? So in other words, I want to retire, right? I want to retire and I want to spend a lot of money per year. I want to spend $500,000 a year, and I'm estimating my retirement will be 20 years. When can I retire? If I can put $2 million in right now or if I can put $2 million in year 1 and then 2 times 1.06 in year 2 and so on, how long do I have to do that before I can just retire and stop investing? So this is a two-part question, because let's draw it out. So this is what retirement would look like, right? Probably a pretty happy, from my perspective, retirement would be $500,000 a year, right? So we're starting here, and we're going to do this for at least 20 years, right? We're going to do this for 20 years. So the question is, how much money do I have to have the year prior when I realize, hey, I'm there. Like, I have this amount of money, I can now retire it, and then next year I'll take that 500, I'll take that 500, I'll take that 500, I'll take that 500, right? So, zoom out a little. So this is the question, right? Like, this is what I want to know. In what year am I going to have that amount of money? But so far yet, I don't know what that amount is. So this is going to be part 1, is to solve for how much money do I need in the bank in order to do this. Part 2 is I'm going to invest over here, how many years is it going to take me before I can retire, right? So let's look at that second part, and then we'll come back to the solution. So this is the second part where I'm going to put in 2 million, and then I'm going to put in 2 million times 1.06, and so on, right? And I'm going to keep going until I get to that x minus 1 year, because here I'm going to have whatever I need in the bank, right? So let's say bank. So this is when my account is set up and I can retire. Right? But what is this amount? What is this amount that I have to have? So let's go look at it. So this one's straightforward, right? We're going to remove 500K a year. So that's just an annual worth. Right? So all I have to do is calculate the total value of all of these. Right? Don't forget there's a bunch of them. So the annual worth that I want is 500K. I want to do that for 20 years. I can earn 6%. So my present worth, which would actually be 1 year before this first payment, right? So P given A, 1 year before the first payment, puts me here at x minus 1. Right? That value, P x minus 1, is going to be this. Right? So from the table, I look up the value, and I solve it, and I realize in the bank I need 5.735 million in order to make this other scenario happen. So once I have 5.73 million in the bank, I can retire and I can take out $500,000 a year for 20 years. Considering I still earn 6% on that money, right? In my bank or in my investment account or whatever. So now we know that this F is actually 5.735 million. But we still don't know what year this is, right? 1, 2, 3, x minus 1. Well, we know one thing, right? We're putting in 2 million plus a year. So I can tell you quickly, right, that the answer is going to be less than 3 years, right? Because in 3 years, even without the gradient, I'll have put in 6 million. So I know it's going to be less than 3, just for, you know, my sanity, so that when I get an answer, I know I'm probably right if it's less than 3. Now, since we're increasing here, right, we're increasing our payments, so this would be 2 million times 1.06 squared, right? Each time, so this is a geometric gradient. So this is a geometric gradient, and I'm going to have to solve it using present worth, which is sort of unfortunate, right? Because what I would like to do is solve future worth of these payments and see where it matches up with this. But I can't because we only have the equations for present worth. Right? So I'm going to have to take that future amount and move it to the present. This is the future amount that I want. And I'm going to have to take, and I could solve this, I suppose, using present worth. But what I'm going to do here is I'm going to say present worth is equal to fx1 pf 6% for n. Right? We don't know what n is. But you see what I'm saying? I'm taking this amount and I'm moving it to the present. Okay. So you should recognize that this equation right here is 1 plus I to the minus n, right? Because we're moving a future amount to the present. So here's what we want to find, right? Or want to have in the bank, and then here is that 1 plus I to the minus n. Right? So this is that, and I'm setting that equal to the value that we solved for earlier. We know we need 5.735 million, and we're going to bring that to present. Right? Why do I do that? Because on the other part of it, right, this is the payments that I'm going to make. Right? We're putting in 2 million. It's a geometric gradient that's increasing by 6%, and our interest rate is also 6%. N is what we don't know. Right? We're trying to find that. So I can go back to my equation, and see that, so I can go back to my equation and see that G is equal to I, right? 6% and 6%. So we're going to use this equation to get the present worth, right? So that's where this comes from. So 2e to the 6th, 2 million times in 1 plus I. Now I can set those equal to each other. So I set them equal to each other, and then I can solve for in, right? And solve for it. So I just threw it into Wolfram and let Wolfram do the work for me. Right, so here's my equation. Hit enter, does various things, and it comes back and tells me the answer is 2.6. Now we're dealing with whole years here, but it should not be surprising that the answer is 3 years from now. So the answer is actually 2.6 years, but if we're dealing in whole years, then we're going to say, okay, 3 years from now, you can do it. You can start taking out that, or getting those payments of $500,000 every year for 20 years. Right? And we knew from the beginning that it was going to be less than 3. Let's do a part B. What if you only put in $200,000 a year instead of 2 million, right? We were going to put in 2 million, but now we can only put in 200K. We're still increasing that amount by 6% a year. So the only thing that's changed is that first amount. So we could, remember before I was saying, like, we know it was 5.7 and some change million, and I was going to put in 2 million, so I knew it was going to be less than 3 years. And I knew it was going to be less than 3. Now, I could do the same here, but instead of 2 million, it's 200,000. And that tells me 29 years. But there are interest effects here, and so I know that 29 years is going to be the limit, way long, and it's going to be something much shorter than 29 years. Right? So how do we solve this one? Everything's the same, except we replace the 2 million with 200,000. Right? So here we are with our 200,000, and we set it equal. This is still the amount we want in order to draw out the $500,000 a year. Right? So this didn't change. The only thing that changed is this. So I go back to Wolfram and plug that in, and I let it solve for me. And it comes back with this. So then I would say, I'm looking at the answer, is 13.7 years roughly. So essentially 14 years from now, you can retire and take out that $500,000 for 20 years. Some of that may have gone too fast, so I encourage you to pause the video and check it out, or rewind it so you can see how these amounts, if you got lost just switching, all we did here was switch the 200,000 with the 2 million, or anything else that's needed. If you have questions, feel free to post them.
You've come up with an overly utopian idea. Look that word up in a minute.
Like a perfect world?
Mm-hmm.
So?
So, what put this idea in your head?
'Cause
Everything sucks.